Hello guys, welcome back. It's been a while. It's been a tough tough month for me. All right, now today I'm going to provide another step-by-step explanations to one of the further maths past year paper. That is November 2020 paper, uh, pure one paper, paper 1-2. Right, now let's get started. All right, welcome back, guys. This is the first questions from the further Pure 1 paper, November 2020. Let's get started with this. The first one, uh, for first questions, the cubic equations given as x cubed plus bx squared plus cx plus d is equal to 0, where b, c, d are constants, has roots alpha, beta, and gamma. It is given that the products of the roots is equal to -1. Therefore, the first part, we need to state the value of d here. Okay, now let's get started with how to analyze these questions uh, more in detail. Right. Now, the usual way is you can actually memorize the formula for the product of roots or the sum of roots, and then you can get your D very easily. So the quickest method, because it's only 1 mark in this case, so the quickest method is we know that the from the property of the cubic function itself, we know that alpha, beta, gamma is basically the same as -D. And then we are given alpha, beta, gamma is actually -1. Therefore, we're going to equate this equal to -1. And then from there, we can conclude that the D is definitely a 1 here, right? So therefore, that is our first answer. So D is equal to 1. All right. Okay. Now, next, I'm going to show you how to obtain um, another alternative methods to obtain the answer for D here. Right? So this is the first method. The second method is we're going to start off from the definitions of this particular cubic function. We can represent that cubic function as um, in the form of factor form of this cubic function. So we can represent the cubic function in the factor form. Now the factor form for this cubic function is written as x minus alpha, x minus beta, and then x minus gamma here. Therefore, this cubic function can be represented in its factored form in this way, and then this factor form is equivalence to this cubic function here. Now, before I try to apply the comparison, let me expand this. Right, expansion shouldn't take you too long in this case. We can just expand it as okay. You can see that this is the expansion for the first part, and then we have x minus gamma. Okay. Next, we're going to expand each one of these. And then finally, we have that products or roots. And then thereafter, Uh, Now, usually before we finalize, you can sort of do a quick check, like how many terms that we are supposed to have. Here we have one, two, three. Here we have two. So we expect to have, like, based on the combinations criteria, we should have six of them. One, two, three, four, five, six. Yeah, we indeed have six, right? Now, I did not check the positive, negative, but hopefully later we'll get it done later on. And then we can use these fundamental definitions to keep a check on our answer that we did here, in case we miss out the positive, negative, right? So from here we have x cubed, and then we can group the like terms together. Here you can see that we have the sum of root, which is refer to the coefficient for x squared, and then we can sum up the coefficients for the x. In this case, we will have alpha, beta, and then lastly, we can actually group up the last term, which is just the product of roots. Okay, just do a quick check in case we miss out anything. Here we have like 1, 2, 3, 4, 5, 6. Okay, we still have the particular six terms that we have. So indeed, we managed to cover all the term based on your group in this case. All right. Now, if you're happy with this, yes, we can compare this with the original cubic functions. Now, this is exactly the same as x cubed plus a bx squared. You can see that. And then after that, plus a cx, and then finally plus a d there. All right. And then by comparison, you will notice that the d is actually equal to negative. By comparison, we conclude that d is the same as negative alpha, beta, gamma. And then alpha, beta, gamma given to us is negative 1. Therefore, we can substitute this as negative, negative 1 here. And then finally, we obtain the answer as a 1. Yes, indeed, we got our d correctly at this point. Right? Now, at the same time, by using this definition, we can obtain the rest of the relationship between the alpha, beta, gamma, and the constant b and c. So here we notice that by comparison, the b is equal to the negative sum of root, and at the same time, the c can be written as the sum or product of the roots, which is given by this beta, gamma. Okay, and then there you have it. This is the relationship that we are getting at this point of time here. All right, now I'm going to pause. That's our first answer using two alternatives method. Of course, um, now there are many other methods that you can use, but these are the preferred methods to use in the exam. Of course, as a student, I likely be choosing method number one, because it only take like maybe less than 2 seconds to actually come up with the solution, and then the effort mark is like 1 mark here. But anyway, for understanding purpose, um, method number two is clearer. Like, you might be wondering where the product of roots actually came from, and then why is it equal to d in this case, right? So I hope that is clear. Now we still have section B for question one. We're going to proceed on shortly. All right, let's move on to second part of this first question. All right. Now the second part state that find a cubic equation, another cubic equations with the coefficients in term of b and c, whose roots are alpha plus 1, beta plus 1, and gamma plus 1. All right. Now, How are we going to do this? Now, of course, there are many methods to do this. I'm going to show you the first method, the more tedious and lengthy methods um, from the definitions that we have found out just now. So first of all, we're going to find the sum of root. So we're going to find the sum of root. In this case, I make it shorter here. I just use a very simple notation just to signify that the sum of the roots as um, alpha plus beta plus gamma. So I just put down as I here. It's the sum of all the roots for this new cubic equation. And then how do we do it? We are basically saying that we're going to add up the first root with the second root and then with the third one. With a bit of rearrangement, we found that this is the same as, okay. And then from what we have found out previously, all right, we notice that the sum of roots that we have derived at our first section there, we found that the sum of root alpha plus beta plus gamma is actually given by negative b. And then at the same time, we also found that the product, the sum or product of roots is given as C here. Okay, and then finally, of course, the I'm going to write that down. Alpha, beta, gamma is actually given as negative D, which is the same as negative 1 in this case, right? And then by using all these criteria and property, we can substitute one of these here. Therefore, we end up with 3 minus B. Okay, now that will be the sum of all these new roots. And then next, we're going to get the product of roots. So I'm just going to write briefly as alpha beta, right? These actually represent the sum of all the products of these new roots, which is alpha plus 1 with beta plus 1, or it could be alpha plus 1 with gamma plus 1, or lastly we can have beta plus 1 with gamma plus 1 here. Okay, now I hope that is clear. Just to have a quick check, right? If we cover all the sum of all the products of roots. Okay, let me check with alpha, beta, alpha, gamma, and then beta, gamma. All right, we are good. And then with a bit of expansion, we will have, okay, sorry about that. I copied, written down that wrongly for this expansion here. This is the first part of the expansion. Then the second part, and then lastly I have, then as usual, we are going to group the product of alpha beta together. And then all its individual sum of roots. I can see that here we have 2 beta, 2 alpha, and 2 gamma. All right, and then finally we have a 3 here. All right, now by using the identity that we have, or the property that we have discovered previously here, we can substitute each one of these here. That will be a C, and then this part is 2 times of the sum of roots, which is 2b, and then finally we add up with 3. And then there you have it. That is the sum of products of roots. And then finally we will have the product of roots. So the product of roots is given by alpha plus 1, beta plus 1, and then finally we have gamma plus 1. And then from here, we're going to do a bit of expansion as usual. We will have, okay, that's how it looked like. And then finally, you can further expand that. Okay, hold on. Just let me rewrite over this side. It will be easier to see. We have alpha, beta, gamma. And then finally, we have our gamma plus 1 here. Okay. And then finally, we're going to group them based on your terms. We have the product of all the individual roots, and then we have the sum of the products. We have alpha, beta, we have alpha, gamma, and then finally we have beta, gamma. Okay, and then lastly, we have the sum of roots plus 1. All right, and then from here, as usual, we're going to substitute that. We know that alpha, beta, gamma is negative d. So this is negative d. And then the sum of products of root is c. And then this is negative b plus a 1 here. Okay, so that's how it would actually look like at this point in time. And then we do know that the d is a 1. We have already found d is actually a 1. And then by using d equal to 1, we can eliminate that with 1. Therefore, we can simplify that into c minus b. Okay, now we have managed to obtain the sum of roots, the sum of products of roots, and then finally we have managed to produce the products of roots. Now we're going to um, collect all these as the coefficients for the new cubic functions that we're going to form shortly. Now before that, I'm going to write down all this information at the side so that we can refer to that more easily. I'm going to simplify this here so that we can refer to that more easily. This is typically a 3 minus b. So I'm going to write that down as 3 minus b. That is our finding. Okay, we don't need this anymore. And then the second part will be the sum of the product of roots is equal to c minus 2b plus 3. And then finally, we have the products of roots is equal to c minus b. All right, now that's all we need. I'm going to clean all this up. Okay, maybe let me change the color there so that we can refer to it more easily. C minus b. All right, now those are the three coefficients that we're going to use for our new equation here. So for our new cubic equation, therefore, we will summarize that the cubic equation whose roots are and gamma plus 1 is actually given by, we can write it down as x cubed, and then it will always be subtraction of the sum of roots, okay, multiplied by x squared, and then after that the sum of the products or roots x, and then finally we have the products of all the roots equal to 0. Now that will be the cubic equations that we are going to form based on all the information that we have already obtained. We just need to substitute that. Here we have 3 minus b x squared, and then the sum of product, which is this, and then finally we have our c minus b. Okay, and then there you have it. That is our equations, our cubic equation that has a roots of alpha plus 1, beta plus 1, and gamma plus 1. Right, now I hope that the first method is clear. It's a bit lengthy, but it does get the job done. Now, secondly, I'm going to present to you another methods, alternative methods, which is more um, preferred methods over this first one, right? Okay. Now, I'm going to erase all. I'm going to show you the second method, how to carry out or find out the cubic equation whose roots are alpha plus 1, beta plus 1, and gamma plus 1 more easily than the first method that we have seen here. So this is our second method. I'll call it second method. Now, using second method, all we need to do is let y equal to x plus 1. So you can always treat the x as representing all the roots of alpha, beta, and gamma. So this is more like a general relationship between the new equations that we're going to form, the new cubic equations in terms of y, and then the relationship between these roots of the new equation y and the original cubic equations in terms of x. Okay, now doing a bit of rearrangement here, we're going to make x as a subject. All right, and then there you have it. X is equal to y minus 1 here. Next, we're going to substitute this equation into the original function here. Now, the original function was plus b x squared plus cx, and then don't forget we have already found the d, which is 1. We're going to substitute this equation x equal to y minus 1 into this original cubic equation. That will be square plus c, and then finally plus 1 equal to 0 here. And then of course you still need to work hard on this because we need to expand this using binomial expansion, for instance. Okay, and then we're going to perform the same routine for the second one. And then finally the last one, c plus a 1. Okay, and then lastly, we're going to group the like terms together. We only have y3 here. I noticed that we do have y square. Therefore, I'm going to group the y square together. Okay, that will be y square. Okay, and then after that, I'm going to group um, the term y together. And then I noticed that we have what are we having? We have negative 2b, we have c, so there's c minus 2b, and then plus with 3. that is the coefficients for y. And then lastly, I'm going to collect all the constant together. I notice that there's a negative 1 and 1, so they will cancel each other. I'm only left with b minus c equal to 0. And then you will notice that this answer is exactly the same as the one that we had previously, or some of you may prefer to write in this form, for instance. It could be written in this form. And then this one, I will maintain it as it is. And then lastly, we can write as CB here. Just to remind ourselves of the alternating sign um, that is related to the roots alpha, beta, and gamma. And then there you have it. Do I really need to convert it to x? Um, it's not an it's not compulsory because this is a new cubic equations anyway. And then x and y, it's just a representations of the variable involved, right? And then there you have it, the same answer that we got using first method here. So I hope that is useful. And then lastly, I'm going to show you the last section for this question. Right, let's take a look at our next question, which is question 1c. I have written down the cubic equations that we have developed from our question B just now, which is y cubed minus 3 minus b y squared plus c minus 2b plus 3y minus c minus b equal to 0 there. I will label that as a cubic equations as A. And then this cubic equation has the roots of alpha plus 1, beta plus 1, and gamma plus 1, just for our reference in this case. Okay. Now from here, we can work out a few relationship between the B and the alpha, beta, and gamma, and the C and so on, right? Now, how are we going to develop the relationship? We're going to recap again. We know that the sum of all the roots, which is given by alpha plus 1, okay, and then this is actually given by we know that from these particular equations here, okay, we can sort of simplify this into, okay, now before I even simplify this, I'm going to make use of what is given to us. I'm going to write that at the side. Given that the gamma plus 1 is equal to negative alpha plus 1, right? So here I'm just going to um, sort of rewrite this in this form. And then from here, we notice that y plus 1 is actually equal to 0. Okay, now that's what is given for us. All right, and then from there, we can summarize this one. We can simplify this. Okay, now I'm going to simplify this part here. And then this can be written as we know that alpha plus 1 and the gamma plus 1 is actually equal to a 0. Therefore, this is only left with beta plus 1 because these two terms here will sum up to 0, only left with this term. And then from this particular cubic equations, we notice that the beta plus 1 is actually given by 3 minus b here. That is the sum of roots. Okay, there you have it. That's the first part. The second part is the sum of products of roots, which is alpha plus 1, beta plus 1, or it could be alpha plus 1, and then after that we have gamma plus 1, or finally we can have beta plus 1 with the gamma plus 1. Okay, and then from here we can do a bit of factorization. We can take out this factor here, then that would give us beta plus 1. And then we notice that from the given properties, the sum of these two roots will be equal to 0. So the sum of, did I factorize it correctly? The sum of, I should have factorizing out the beta one. Okay, sorry. Just let me, that defeat my purpose here. Okay, just let me refactorize again. I think my intention is to actually factorize this part here, these two. Okay, now I'm going to do that one more time. I'm going to factorize that beta plus 1. Okay, now there you have it. And then we notice that the sum of these roots is equal to 0. Therefore, this part will be equal to 0. Eventually, we end up with this part here, that is alpha plus 1 and gamma plus 1. And then we also know that gamma plus 1 is equal to negative alpha plus 1. Therefore, you can further simplify this as negative alpha plus 1 if you want. Okay, and then we know that the sum or product of roots is actually equal to c minus 2b plus a 3 here. Okay, now that's how it look like. And then lastly, we're going to work out the products of roots. Okay, so the products of roots is alpha plus 1, beta plus 1, and then finally we have gamma plus 1 here. Okay, and then we know that beta plus 1, which we have already found out from here. Okay, you can see that I'm going to put a bracket here so that you can refer to again. Beta plus 1 is actually 3 minus b. Therefore, we can rewrite that as 3 plus b, sorry, 3 minus b. And then alpha plus 1 and gamma plus 1 multiplied together is basically this one here. That is negative alpha plus 1. That is the multiplication between these two roots. And then multiply with beta plus 1, which is 3 minus b. Okay, this is square. I forgot to put the square there. Okay, we are almost there, right? So from here, I'm going to highlight the one that we need. Again, this is the one that we need at this point. You can see that this is one of the relationship. And then we also have this one here. Okay, we also have the second relationship, and then the third one. The last relationship tells us that the products of this must be equal to, from the cubic equations, we notice that the product of roots is actually equal to c minus b here. Okay, and then we are almost done. All we need to do is just compare this equation here with this equation here. We can take, if you want, we can simplify these two equations. All right. So let's assume that these are the two simultaneous equations, and then we can simplify it by taking, uh, how should I put it? Okay. You can actually, let me see, we can take 2, for instance, divide by 1. We can take the equation 2 divided by 1. Therefore, what is left is this. become 3 minus b equal to, so that is only 3 minus b, equal to c minus b divided by c minus 2b plus a 3. Okay. And then for this, you can also rewrite as this. You can actually make it the same as the equations that we want to prove in a while. They are using b minus c, but we have c minus b, 3 minus b here. You can actually apply negative both sides. That would actually give you b minus 3 equal to b minus c over c minus 2b plus a 3. Therefore, we can conclude that um, b minus c minus 2b plus 3 multiplied with b minus 3 is equal to b minus c. Therefore, we managed to prove this here. All right. So I hope that is clear at this point. All right. And then there you have it. That is the complete step-by-step solutions to first question. All right. Okay. I'm going to pause here. We will move on to second question shortly. All right. Welcome back to our second question. This is a mathematical induction. We need to prove by using mathematical induction that this expression is divisible by 12 for every positive integer of n here. Okay. Now let us put in certain notations before we start to walk through the steps for mathematical inductions. Usually, I would let P be called the Pn to represent this proposition. All right. So this actually represent. I can say that this actually represent 7 to n minus 1 here. Okay, I would say that this proposition is true. Okay, this is propositions that represent that this expression is divisible, or I can simply write that this is typically the multiple of 12 here. So it can be like 12 multiplied by a k is a multiple of 12 anyway, divisible by 12, where the k are all k and n. In this case, both the k and n are all positive integer, right? Are all positive for all value of n that is positive integer. All right. Okay. All right. Now I hope that is clear. That is our definitions for this proposition. And then to start with this, we are going to start off by checking the first condition. Um, for instance, if we start from n equal to 1, what would that be then? So therefore, in this case, if I substitute 1, that will be 2 minus 1 here. That is typically 48. Is basically 12 times a 4 here. Therefore, we know for sure that this is divisible. So we know that therefore it actually conclude that this P1 is divisible by 12. Okay. Now that is the first check. And then after that, the next part is our induction section. We will make assumption that we will assume that pk, which is given by 7 2k minus 1, is divisible by divisible by 12. In this case, since I'm using k already, so I may not want to use k. You can use any symbol you like. So take for instance, since it's divisible by 12, I just write down p, where the p are all positive integer. All right. Okay. Now that's a start, and then assume that this is equal to this. This is divisible by 12, and then we're going to carry out the inductive process of pk plus 1. Like we want to find out whether the next term for this expression is divisible by 12 or not. All right. So going through this, it basically means 7 2k plus 1 minus a 1 here. Okay, right? Will this be divisible by 12 or not? Okay. Now, the best thing or the easiest way to deal with this is we will label this as our first equation. This will be our second equation. By taking the second equation, subtract off with 1, we found that pk plus 1 minus pk here is actually equal to 7 2k plus 1 minus a 1, subtract off with 7 2k minus 1. All right, and then from here we can factorize out. We notice that this is the one that we have, 7 2k here, and then you can do a bit of factorization. Up to you how you want to deal with this. We can factorize the 7 to about 2k, and then that is only left us with 7 to the power 2 minus a 1. And then that is a very clear evidence to show that this expression is divisible by 12, because we know that this is 48. So this is 7 2 k. This is 12 times 4 here. And then therefore we can imply that pk minus pk here is divisible by 12. It is divisible by 12. And then you can also rewrite this as pk plus 12p. We have already made an assumption at the beginning saying that pk is divisible by 12. Since pk is divisible by 12 and then 12p is divisible by 12 also, therefore we can conclude that pk plus 1 is the divisible, okay, divisible by 12. Okay, right? And then knowing that pk plus 1 is divisible by 12, this imply that pk is also divisible by 12. All right. And then finally, by using principle of mathematical induction, we notice that P1 is true. True here means it's divisible by 12, and pk plus 1 implied that pk is divisible by, oops, my writing keep on missing a lot of letters here, divisible by 12. Okay, therefore we can conclude that Pn equal to 7 to the power n is divisible by 12 here. All right, now that is how we apply the process of mathematical inductions to prove that this expression is divisible by 12 for every positive integer of n. All right, now I hope that is clear. I'm going to move on to the next question shortly. All right, third question. By simplifying this expression, we need to prove that this expression can be written in such a way. Okay, now that is just a one mark question, so we would expect that it is not really that difficult to work on. Okay, let's just follow the rules here. All we need to do is just carry out the expansion process. That should not be any problem here. All we need to do is just expand this. I'm going to rewrite this as xn. Okay, let's try to expand this. You can see that this is not a tough one to work with. You can apply the strategy of I would say that is something like uh, a square minus b square. You can actually do that. If you're not very comfortable, you can just expand it one after another in this case. So take for instance, if you are very um, not very sure of how to apply that identity, we can just expand it manually. So here it will be xn multiplied by xn. We have 2 n here, and then after that we will follow up with xn. So that will be here, and then after that we're going to subtract off with xn here. Okay, now that's our second term, third term, and then the last one we will have x2n plus 1. Because both of them are square root, therefore we will have this term as x to the power 2n plus 1. Okay, and then from here is quite easy to see that all these terms sort of cancel out each other, and then eventually you're only left with a 1. So this x2n cancel with this cancel with this, and then the final answer is, oops, sorry, it's supposed to be a negative 1. I miss out my negative, right? So that's negative. And then I'm going to rewrite what we have. We found that xn minus x2n plus 1 multiply with xn plus x2n plus 1 is actually equal to negative 1. Okay, and then with a bit of rearrangement, for instance, you can rearrange it in such a way how you want to put it is entirely up to you. So one way to do it is, let me see how you want to put it. Okay, we can actually apply this negative 1 directly onto here. So what I mean by that is this one here, we can actually rewrite xn plus x2n plus 1 like this is equal to negative 1 over xn minus x2n plus 1. Okay, that's how it would actually look like at this point. And then you can multiply both sides by negative 1. So if you multiply both sides by negative 1, it will be xn. Okay, And then finally, we can sort of replace this in a different order. And then we found that 1 over xn minus x2n plus a 1 square root is the same as negative. If you expand this into that expression, it will give us x2n plus 1 square root. All right, now we managed to prove that. We managed to prove this equation. Just double check one more time. Let's see whether that is correct. If we miss out anything, yep, that is correct. We are happy with this, so we will write down yes, proven. Okay, now I hope that is clear for our first part. Stay tuned for the second part. All right, section B of this third question. All right. Now we have to recall what we did for our first section just now. We managed to prove that 1 over xn minus x2n plus 1 here is given as negative xn negative x2n plus 1 square root. Okay, this is the relationship that we have proven from our first question A. Now we might have to make use of this in this summation of this particular sequence using methods of differences. So for this purpose, I'm going to rewrite my un. I'm going to make use of the proof that we have obtained previously. Therefore, the entire expression can be written as this section. We can replace that with okay. Now that's how it look like. Now the sum of, we need to find the sum of this sequence here. The sum starting from 1 to n. Okay, we can start from having n equal to 1. If you have n equal to 1, you will have x squared plus x to the power 4 plus 1, and then continue on with x1, and then x squared plus 1 plus. Okay, now that will be our first sequence, and then we're going to continue on with the second sequence when n is equal to 2. Therefore, when n is equal to 2, you have 3. Okay, and then continue on with n equal to 2. Okay, and then we have x to the power 4 plus 1. And then continue on with the next term. If you want to know more about the patterns that will arise, maybe it's best we put in another term here when n is equal to 2. So, hold on, this is n equal to 1, n equal to 2. We're going to try n equal to 3 now. Okay, and then you will notice that some of this term can be eliminated. This term here can be eliminated by this term. This term is done, and then you also notice that this term can be cancelled out. And of course, you can further apply the telescoping effect to cancel off all of this term here. And then we're going to proceed on until the term n minus 1. We're going to let n equal to n minus 1 at this point. So I'm going to let n equal to n minus 1, the second last term. That will actually give me an n plus, okay, now that will be x2n plus a 1, and then after that I will have x n minus 1 minus x2 n minus 1 plus 1, and then I'm going to keep on summing up the n term until the n term. So when n is equal to n here, I will have n plus 1, okay, n plus 1 plus 2, plus 2 plus x, x to the power of 2n plus 2 plus a 1, and then finally I will have my xn, subtract off with x2n plus a 1. Okay, again, you will notice the same patterns arise. So these sections can be cancelled out, and then this part here can be cancelled off with the previous term. And then what is left behind is the entire summations can be written as un now, starting from n equal to 1 until n, can be written as, we only left with this term and this term. Therefore, I'm going to write that down as n plus 1 plus x2n plus 2 plus a 1. And then after that, subtract off with my xn. Oh, hold on. Just let me rewrite again so that I can position it nicely here. So we are interested in getting the sum of n here, starting from 1 to n. That will be the same as xn plus 1 plus x2n plus 2 plus 1 here. And then finally, we're going to subtract off with the first term. That is x2 plus 1. All right, and then there you have it. That will be the sum of n term for this sequence in term of n and x, right? So I hope that is clear for your understanding for section B. I'm going to finalize the section C shortly. All right, section C of this question 3, I have rewrite the sum of the sequence that we have already derived just now. This is the sum to n term. All right, now this question state that deduce the set of values of x for which the infinite series u1 plus u2 plus u3 and so on and so forth is convergent, and give the sum to infinity when these actually exist. Okay, now how do we know when will this converge? You can actually give it a trial error, for instance. There are only few conditions where we can actually apply onto this sum of n term. So you can say that let take for instance we try let us try x that is equal to a how do I put it, x more than 1, for instance. Let's try x more than 1. Okay, if x is more than 1, okay, now therefore what happened to this what will happen to this sum as the n is approaching infinity? That's the one thing that we want to check. As n approach infinity, what will happen to the sum of this sequence? So we give it a try as x is greater than 1, meaning that is like number 2, number 3, and so on for x. What will happen to this term? You will notice that when n is getting larger, we notice that the x n plus 1 would approach infinity. And then the same go for this term also. Therefore, this will also approach infinity. Whereby this is typically a constant. You are actually taking an infinity, subtract off with very small values here. That would eventually lead us to the sum of this n term, n equal to 1 to n, um, is approaching infinity. Therefore, we don't have we can conclude that in this condition, for these conditions when x is greater than 1, the series di diverges. So the series diverges. It does not converge. Okay. Now, therefore, we're going to try something else then. So why don't we try something like x is between -1 and 1. This one reminds us of binomial expansion. If you still remember, for binomial expansions, the value for the x itself usually lying between -1 and 1. Okay, why is that so? Because any value lying between -1 and 1 is a proper fraction. It's a proper fraction. So therefore, in this case, as n approach infinity, because this x is a fraction, example like 1 over 2. So you just for just as an analogy itself, I'm going to write down here for some of you to visualize it. Take for instance, if x is like 1/3, so that as n is getting larger, you have 1/3 to the power of infinity, for instance. What would that lead you? You can actually give it a try. So this would typically be 0. This would eventually um, converges to 0, and then the same go for this, and then eventually this would become a 1. Okay, and then as I mentioned before, this is still a constant. Nothing much is going to change here. Therefore, the condition, the set of value of x for which the infinite series is convergent. Okay, so we'll write down series is convergent when x is lying between -1 and 1. Okay, right. Now, it diverges when the whole series approach infinity. It converges when the series approaches a fixed constant value, which is in this case is given by now sum to infinity. So we're going to find out what is the sum to infinity as n is approaching infinity. So we're going to use the limits here. So that's typically saying that when n is approaching infinity, what will happen to this series? Now we know that at this point that is the same as limit as n approach infinity x n plus 1 plus x 2n minus x minus x squared plus 1. Alright, now we know that as n approach infinity, I have already shown you one of the analogy. If the x value fall within that restriction here, then this term x to the power n plus 1 would converge to 0. This term will also converge to 0. I'll highlight the term that will converge to 0. These two terms will converge to 0. And then therefore, this entire series would converge to, this would become a 1 minus an x minus x squared plus 1 square root. Bear in mind the x minus x squared plus 1 is basically a constant. So therefore, the whole series will converge to this expression provided the x is restricted between this interval here. Right? So I hope that is clear for question 3 here. All right, next question 4. This is matrices and transformation. All right, let's read through this. We have the matrices A and B given by these two by two matrices. All right, we have A and B given as such. The first question, we need to give a full details of the geometrical transformation in the xy plane represented by A. Secondly, we need to give a full details of geometrical transformation in the xy plane represented by B. Now here I have already prepared two axes to answer these two questions here. Now the best way to answer this, or of course, there are some students that actually memorize the structure of the matrix that give them that particular transformation. Yes, can you do that? Of course you can. All right. Now, anyway, for myself, I can't actually memorize all this. So what can I do then? All right. Now you can choose a unit square. Right. So that unit square usually start from O here, and then it's 1 unit long. So we start from like 1 unit here, and then 1 unit here. So because it's 1 unit square, all right. So you can actually draw the square here, for instance. Right. That is your 1 unit square, and then this is 1 1. So we have this coordinate here. This is 1 0. This is A, and then we can call this the B, which is 1 1. You can write in a matrix column form. Okay, maybe I try to standardize all this. We try to write that in a matrix form. Okay, that is A 1 0, and then this one we'll call that C then, which is 0 1. Okay, now once you establish your unit square, we're going to perform the transformation. All right, now how does it work actually? All we need to do is we will choose that particular point. For instance, A. When we want to transform the A under this transformation, okay, we do have a A here. This is a A here. Okay, anyway, bear in mind this A is a transformations matrix. This A is the sort of the position on the Cartesian plane, right? To transform this A, I'm going to write down the image. So the image A under this transformation is written as 0 1 1 0. We are going to transform this. We're going to look at where is the image for this transformation. So by using a calculator, or you can do a manual calculation here, should not be a problem. It's very obvious. The first one is a 0 and 1. So what does that mean? It means that this particular object A is being transformed to this image 0 1. So therefore A 1 0 end up at here. So we're going to label that as A prime. So A has been transformed to this image. And then next, we can try to transform B. Okay, if you like to transform B, for instance, I just use the same symbol here just to save time. You want to transform B. Okay, that is also quite obvious. It's a 1 and then a 1. So to transform B, B will still stay at the same location. Let me see whether that is correct. Yep, correct. So B will still stay at the same position, and then we can label that as B prime. So B is transformed onto B itself, but A is being transformed to A prime here. Okay, and then next you can also try for the next position. So for C, let's try to transform C then. I'm going to write it down over here. I'm going to transform oops, this one is for B. I wrote it down wrongly. Hold on, just let me change the image is B. I wrote down wrongly. And then now I'm interested to transform the object C, and then so that we can get the image C prime here by performing the same routine, that is 0, 1. Let's see where this object um, is being transformed to. From here is also quite obvious. It's a 1, 0. So it means that C prime has been transformed back to, sorry, C has been transformed to 1, 0. So this is where the image for C is located. All right. Now from here you can indirectly see that it's some sorts like a reflection. Yeah, like A is reflected on the other side, and then C is reflected here. But what type of reflection is that? Okay. Now you can see that B does not change itself. Therefore, the reflection must be something here. Just let me draw it roughly. It look. Oops, it got overboard there. Let me shorten it then. Okay, be patient with me on this. Okay, I hope it works. I hope it works. Okay, it's something like that. It's not so accurate. The line is actually a reflection. So I'll just write this one down as this is a this line has this equation y equal to x. So you can see that this is basically a reflection in the line y equal to x, or you can say that this is a reflections about the line y equal to x. Therefore, I'm going to finalize that. These types of transformation is a reflection in the line y equal to x. Okay, and then there you have it, right? Now, generally, you don't really need to test out so many points just to figure out this is a reflection. Mainly, you can just use A and C just to find out that what sorts of transformation is this, right? Okay, now I hope that is clear. Now that is A. Now for B, okay, I'm going to write this one down. This is the answer for A, and then for B, the transformation matrix is given here. Now we're going to repeat the same routine here. We're going to label this as A also. So maybe this one I'm going to label it as P then. Let's use a different letter instead. P, and then you have another one here as the Q, that is 0, 1. Okay, and then you can actually draw your unit square if you like. And then you have another point here that is, let's call this R. Doesn't matter how you want to label them, as long as it look clear to you and to the examiner, then that will be good enough, right? Okay, now from here we're going to transform this particular point. Let's start with transformations of P then under this transformation matrix. So let's do P prime. So we are going to find out where is the image for this P under this transformation. That is negative 2, 1 over 2. Okay, and then P is 1, 0. And then that shouldn't be that tough. It's just half here. I think it's a half. Yep, it's a half. And then after that you have sec 3 over 2. And then that's it. So this P here will end up at somewhere like half. Okay, somewhere half. And then we are looking at this is 1 point something, 0.5 around there. So it end up at somewhere here. I think it should be somewhere here, for instance. Yeah. Okay, this is our P prime. This is where our P prime is located, right? And then just to make it clear, this image is located somewhere here. It's half a unit, and then set 3 over 2 here. Okay, now that's how the image actually look like. And then next we're going to transform, like you can try transforming Q, or you can try transforming R also can. Now in this case I want to make it simple a bit, so I just transform the Q then to get the Q prime. Same thing. Now I'm going to transform the Q itself, which is 0, 1, and then that would give me like negative 3 over 2, and then one more is at 1 over 2 here. Right, and then I just need to mark it on the Cartesian plane, and then let's see that in this case it will also be somewhere here, but it's kind of like a negative um, negative um, 3 over 2, and then a half. Okay, so this is our Q prime there. That's our Q prime, right? And then from here, we sort of notice that it's kind of like a rotation. If you knew that there's rotation, then we will write down rotation. Write down the name for this transformation first. And then when we talk about rotation, it must be rotation of how many degree, clockwise or counterclockwise in this case, right? Now to find the angle itself, you can label this as theta. You can also label this as, you can try to label this as alpha also, assuming that we are not sure whether both of the angles are the same or not, just out of curiosity. You can try out from here, like for instance, the theta is, we can obtain the theta by having tangent theta equal to sec 3 over 2 divided by 1 over 2. And then that would end up with sec 3. And then if you key in your calculator, you notice that this is typically 60 degree. Yeah, it's a 60-degree rotation. And then you can also try out the alpha as well. So by looking at tangent alpha, that would be, I'm just taking the magnitude itself. So you can see that it's sec 3 over 2 over 1 over 2. You will also notice that the alpha is typically 60 degree. Now we can confirm that the alpha and the theta is the same. So indeed it is a rotation of pi over 3 radian, whether it's counterclockwise or clockwise. In this case is counterclockwise. Right, so counterclock. And then don't forget, rotation of pi over 3 counterclockwise, about way. There must be the pivot point where this rotation is being carried out. Rotation of pi over 3 radian counterclockwise about the origin. In this case, this is the pivot point about the origin. Okay, now I'm going to pause there. This is the typical way to discover the types of transformations that you are actually having, right? Now I hope that is clear at this point. I'm going to move on to the rest of the sections for this question 4, right? Stay tuned. All right, let's get back to question C now. We are still on the same question 4, section C. Show that the triangles DEF and PQR have the same area. Okay, now to make things simple for us to work through this, you have to remember the relationship between the determinant, the area of the object, and the area of the image is this one here. This is their relationship. Okay, let's just let me show it to you. Area of in this case I would say the area of image is the same as determinant of the transformation matrix. I'm just going to generalize this transformation matrix as M, for instance. Now, don't forget, determinant could be a positive, could be a negative. Area can only be positive, therefore we're going to put down a modulus sign here. Area or image is the same as the modulus of the determinant of the transformation matrix multiplied by the area of object. Okay, and then there you have it. That's the fundamental formula that we're going to use to answer this question here, right? Now, first of all, the transformation matrix that we are looking at is AB. So the transformation matrix M is AB. Therefore, we're going to work out the multiplications between these matrices. Now, that is A, and then B, we have it here. That's a negative. All right. Now, by multiplying this, we have the first one being cert 3 over 2. And then the second one has been half. And then we're going to continue on with half. And then lastly, we have negative 3, cert 3, sorry, over 2. Okay, just let me check one more time. Okay, that is good. And then that is our transformation matrix here. Alright. And then we are interested to find out the determinant based on this general formula. Now, the determinant of M. Okay, how do we find the determinant? Is AD minus BC. So I'm going to label this. This is sort of like A. This is B. A, B, C, D. AD minus BC. AD minus BC. Let me check if I label it correctly. Okay, I think the labeling is a bit off if I were to use that labeling. Usually we label it as A, B here, sorry. This is B, this is C here, this is D. Okay, this is how it looks like. And then from the formula of determinant, we know that it is given as AD minus BC. Therefore, we have AD here. That would actually give us a negative 3 over 2. You can see that negative 3 over 2. Subtract off with the multiplications. Oh, sorry. I think I multiplied wrongly. Hold on. Here we have a 4. 3 over 4. Subtract off with 1 over 4. And then that would actually give us a negative 1. Okay. Now, because the determinant, the absolute value of the determinant is 1, right? So that therefore we can say that the area of the image, the image that we are looking at is DEF is transformed by this AB onto the triangle PQR. Therefore, the area of triangle PQR is our image, and then this image is the same as the determinant, the modulus of determinant M multiplied with area of object. So the object in this case is DEF. Okay, and then because the absolute value of the transformation matrix here is 1, therefore we can conclude that because the absolute value of the determinant M is equal to 1, therefore we can conclude that area of the triangle PQR must be the same as area of triangle DEF. Alright, now I hope that is clear. I'm going to move on to the next section shortly. Alright, section D of question 4 now. I have just copied down the transformation matrix for AB. I label it as M previously, so I'll be using M throughout this question here. Now the next question state that find the matrix which transform triangle PQR onto triangle DEF. Now let's look at what is going on first. Now first of all, in order we're going to look at the first section here. Is mentioned that the triangle DEF is transformed by this transformation matrix M onto triangle PQR here. Okay, now that is how it looked like. I'm going to just write it down. AB, this is M transforming the triangle AB. Okay, triangle AB. So this is transforming the. I'll just use a short form, transforming the triangle DEF, DEF here onto the triangle PQR. So you can treat this as the object. We are transforming the object based on this transformation matrix M to get the image as the triangle PQR here. Now we want to find out how do we find out the transformation matrix that we're going to use to transform PQR back to its original object. Okay. Now to do that, I'm just going to label this as X. This is as Y then, so it'll be easier to refer to. So basically, MX is equal to Y. In order to work out the matrix that transform Y to obtain the X, all I need to do is just introduce the inverse matrix on the left hand side and then introduce that on the right hand side of the expression at the same time. And then we know that by having this together, it will give us the identity matrix X. Okay, from here we can finalize that X is given by the inverse matrix of M multiplied with a Y there. So therefore, what are they actually asking? They are asking for the matrix that transform the triangle PQR, which is this, onto triangle that. And then the matrix that they are referring to is actually this matrix here, which is the inverse matrix of M. So now we're going to find out the inverse matrix of M. Now, inverse matrix of M is given by 1 over determinant of M, and then we're going to rewrite this, rearrange the position. We know that this is A, this is B again, this is C, and then this is labeled as D. Therefore, we're going to interchange these two positions and then apply a negative onto these two. And then there you have it. That's how we obtain the inverse matrix for M. Now we're going to try this out. First of all, we're going to work out the determinant M. So determinant M is basically negative 3 over 4 minus 1 over 4. I'm just trying to recalculate that again. We have indirectly obtained that just now. It was negative 1. Okay. And then therefore, we can conclude that the matrix required here is 1 over negative 1. Okay, apply this here. That will be negative 3 over 3 over 2. And then we have that negative half. This part will be negative half. and then this would be Z3 over 2. All right, and then just simplify that. We have Z3 over 2, 1 over 2, and then finally we have 1 over 2 negative Z3 over 2. And then there you have it. We are done. We have discovered the matrix that can transform the triangle PQR onto triangle DEF. All right. Now I hope that is clear. I'm going to move on to the next question, next section for this question 4 shortly. All right. Let's look at the last sections of this question 4. Okay. You can see that we are still looking at the transformation matrix of AB. For this E, we need to find the equation of the invariant lines through the origin of the transformation in the xy plane represented by AB. Okay, now I have rewrite the transformation matrix AB for our reference. We have computed this in our previous section. Now, just a bit of information on the invariance line. Now, take for instance, if you have a point, um, if you have a point somewhere here, for instance, this is like um, like a T, for instance, and then let's assume that this is a reflection, a types of reflections transformation, and then let's assume that the T is reflected over here. Now, bear in mind, this explanation has nothing to do with this transformation matrix. I'm just making a general example, assuming that these are reflections in the line L here. The object T is reflected onto T prime here. All right, and then let's assume that the T has the positions of x, y, whereby T will be x prime, y prime, the image itself. Okay, and then you will see that this line here, this line that consists of the 2 points, the object and the image itself, this line is known as the invariance line. Okay, just for our reference here, this is known as the invariant line. Okay, all right. Now that's a bit of the info for this invariance line. Now we're going to hop on to this question now. We're going to solve this. Right? Now, based on the idea of the invariance line, we know that under the transformation matrix AB, which I have labeled as M, so we're going to transform the object here, and then we will end up with the image x prime and y prime. All right, now that's how it looked like, and then I'm going to put in the matrix transformation matrix that we have tabulated, and then that will be okay. And then from here we can form a set of simultaneous equation, and then that sets of simultaneous equations will look something like this. We have x prime is given as okay, now that's how it looked like. And then based on this diagram here, we know that the point, the object, the y coordinate of the object also lie on the invariance line. And then let's call this invariance line as y equal to mx, because we know that this invariance line passes through the origin. Therefore, we don't need to include the y intersection C. So we can simply call it y equal to mx. And then at the same time, this invariance line also consists of this image, and then therefore you can also label this invariance line as y prime is also found on the invariance line having the same gradient x prime here. Okay, so we're going to make use of this. The first part, y equal to mx, we're going to replace the y using mx. Therefore, we can write this as half mx. Okay, and then right after that, we can, of course, you can sort of factorize this if you like. That is typically m plus search tree. Is it m plus search tree? Let me see. Yep. So it's m plus search tree x. And then repeating the same process for y prime, we find out that from this matrix, our y prime will be half a x minus search 3 over 2y. Okay, and then replacing y with mx. Okay, and then we can factorize that one more time. Okay, and then lastly, we also know that the invariance line also consists of the image. Therefore, the relationship between the y coordinate and the x coordinate is found here. Therefore, we can rewrite this as y prime, yes, is equal to m multiplied by x prime. But what is our x prime? Our x prime is given by this. Therefore, we can rewrite that as half m and then therefore that will be y prime is m x, so this is x prime. There you go. Okay, that's how it look like. And then we notice that the y prime is also given by this, therefore we can equate both of these. Through comparison, we can simplify this as, okay, now we can take out the 2 there. That would give us m equal to 1 minus search 3m. Okay, and then all we need to do is just solve this equation simultaneously. Sorry, I think what I meant is solve this quadratic equation. Sorry, it's not a simultaneous equation. Sorry about that. We just need to solve this quadratic equation. Now, why is it a quadratic equation? We can check this out. If you expand that, you get m squared, and then we get to combine the like terms together. We have 2 cert 3m, and then finally we have that -1 equal to 0. Okay, now I'm going to solve it over here, this side here. By solving this, you will find that your m is actually equal to -2 cert 3 plus or minus, we have a 412 plus a 4 here divided by a 2, and then that will give us that is a 4, there's a 2, therefore we have negative cert 3 plus or minus a 2 here. And then knowing the m, we can finalize the invariance lines. There are 2 invariance lines. We know that the invariance line is actually given by this section here. Y is equal to mx. So all we need to do is just substitute the m that we have obtained. Therefore, we have 2 invariance line. The first one is y 1, okay, or I just rewrite as negative cert 3 minus 2x, or we can have another one as y equal to cert 3 plus 2x. Now, therefore, that is our invariance line. I'm going to highlight it here so that it's clear. Okay, and then there you have it. I hope that is useful explanations for your understanding of what is invariance lines. Okay, I'm going to move on to question 5 shortly. All right, let's look at question 5 now. Okay, this questions is polar coordinates. Okay, right now I have prepared the grid at the side here for us to draw the polar curve. Now the questions sounds like this. The curve C has a polar equation r equal to ln 1 plus pi minus theta, where the theta is restricted between 0 to pi radian. Now we need to sketch the curve C and state the polar coordinates of the point of the curve furthest from the pole itself. Right now, just to clarify that, the pole itself is basically the origin. Right? Now, before you can actually sketch the graph itself, the polar curve, we need to plot in a few points just to gauge the shape of this polar curve. Right? Now I'm going to write down the data that we're going to choose in a while, and then after that we're going to tabulate the R itself. Let's try to choose like data equal to I have already chosen like this is pi over 4, and then you have your pi over 2, and then we have your um, is 3 pi over 4 here, and then finally we have this part here is 0, and then this is a pi. Now the length for this is roughly, I'll put that as 1 unit long here. This is like 1 unit. This is 1 unit. This is 1 unit. 1 unit also here and here. Right, whereby this one is 0.5, just as a reference. So I put it down as 0.5, 0.5, 0.5 here. Okay, now we are sort of ready. We're going to choose like data for pi over 4, and then we can go for pi over 2, and then next what else we can have? We can have 3 pi over 4, and then lastly we can have the pi there. Right, for each one of these calculations, for theta equal to pi over 4, now we're going to tabulate the value for r, that is ln 1 plus pi minus pi over 4, and then that should give us ln 1 plus 3 pi over 4. Okay, now if you try to tabulate using your calculator, just let me give you a try. In this case we have 3 pi divided by 4. Okay, and then from there we are going to calculate the ln itself. Ln for 3 point, let me try. Okay, so from my calculator is that is 1.2. Okay, I put it as 1.2 or 1.21 there, because this is just an estimate, I would say. So we're going to put down 1.21, and then we're going to proceed on with theta equal to pi over 2. The r will be ln. I'm going to take a bit of shortcut here. So if you put down pi over 2, that definitely is going to be pi over 2 then. Okay, and then from here we have, let me see what do we have here. Pi over 2 here. So pi over 2, we have 0.94. Okay, so this one is 0.994. And then after that, we're going to proceed on with theta equal to um, 3 pi over 4. That will give us a ln 1 plus pi over 4. Okay, let's see what do we have here. Pi over 4. So pi, and then that will actually give us 0.58. In this case, it's 58. And then lastly, we have our pi. Oh yeah, I forgot to actually include the 0, right? Anyway, I'm going to calculate over here. I think I missed out the easiest part there. Okay, never mind. We try to work out this pi here. Sometimes it does happen. Now from here we have a ln 1 instead. As we substitute theta equal to pi, we get a ln 1, which is a 0. And then the last one that I need to include is theta is equal to 0. So when theta is equal to 0, I will have r equal to ln 1 plus pi. Okay, so just for ease of comparison, that is 1 plus pi. That will give me 1.42. Okay, now I'm ready to plot this. I'm going to start off from like 0. Okay, so when theta is 0, it's 1.42. So roughly 1.42. This is 1. This is 1.5 here. So roughly it'll be 1.42 is around here. So I just tabulate that, and then that would actually give me a ln 1 plus pi here. Okay, so I got my first point here, and then next I'm going to proceed on with 45 degree, which is 1.21. So this is 1.4 something. 1.21 most probably will be closer a bit over here. Alright. And then after that, I will start off with 90 degree, 0.94. So 0.94 should be somewhere here then. And then after that, I'm going to proceed on with 0.58. This is 0.58. So most probably it's going to be somewhere here. And then lastly, when theta is equal to pi, is equal to 0 there. And then I'm going to sketch this graph. Okay, now let us see here. It starts off from here. Alright, you can see that. Oops, sorry. Let me redraw that again. I started off halfway there. So from here, you can see that the curve basically go from here. It will join with this, and then after that go down over here. So most probably the shape of the graph would look something like this. Okay, I think accident happened over here. Okay, yep. Of course, for your case, you will draw it more smoothly, I think. Okay, okay. I think there's something wrong with my drawing tool here. Just let me touch it up. This is a bad, this is a lousy drawing. Okay, it really doesn't work correctly on my panther here. Just let me cut it off. Okay, I hope that will be okay. But for yourself, you will be able to sketch it nicely. Okay, and then there you have it. That is the shape of the curve that we intend to get here. Right. All right. Now I hope that is clear. The proper way to sketch this is to highlight some of the points that we can work on, and then try to draw a few circles on your polar curve so that you can gauge the distance from the pole itself. Right. And then lastly, don't forget, we need to find out the point on the polar curve that is the furthest from the pole. You can see that from here it's quite obvious that the point that is furthest from the pole itself, this is the pole, is actually this point. Therefore, the point furthest, right? The point furthest from the pole is actually equal to ln 1 plus pi a 0. Now that is this coordinate here, right? And then that complete our first part of this polar curve. I hope that is clear. I'm going to move on to the second one shortly. Okay, question B here. Um, Now, using the substitution u equal to 1 plus pi minus theta, or otherwise show that the area of the region enclosed by C and the initial line. Okay, some of you might be wondering what is initial line. This horizontal line is called the initial line. This part here is a pole, just for you to know that. All right, now using this substitution, we're going to show that the area enclosed by this curve and its initial line, which is basically this area that we are looking at. So we are interested to obtain this area. Okay, now how are we going to obtain this area here? Very simple. We're going to obtain this area using the area formula and integration. So area of the based on my drawing, area of the shaded region represent the area enclosed by the curve C, and the initial line is given by the formula half r square d theta. So we're going to integrate that from, of course, the starting point will be here. The lower boundary is 0, the upper boundary is pi. 0 to pi. Okay. And then what is r? We know that r is equal to this. Therefore, we're going to substitute that. That will be entirely become 1 plus pi minus theta. And then the entire ln, we have to square that, d theta, and then integrate that from 0 to pi. Okay, now that will be the area of the shaded region that we are supposed to work with. And then from here, we need to use these substitutions. So using this substitution, u equal to 1 plus pi minus theta, we have du equal to negative d theta. So du is actually equal to negative d theta. And then from here, we will get this part here, half. And then furthermore, because we are using a different lower boundary and the upper boundary after we've done the conversions, we can actually substitute the theta equal to 0. So for theta equal to 0, what could be the u? So theta equal to 0, the u is 1 plus pi. And then when theta is equal to pi, the u is equal to a 1. Okay. And then from here, we will get a negative because there's a negative there. That is from 1 plus pi to a 1 here. And then we are actually integrating ln u square du here. And then for your informations here, if you want to get rid of this negative, you can actually rewrite as this. That is typically 1 over 2 ln u square du from 1 plus pi to 1 here. Okay. Now that's the same as integrating from 1 to pi. if you want to change the negative, if you want to drop the negative, you can actually interchange the upper boundary and lower boundary here. Okay, now from here we need to apply a bit of integrations by parts. Okay, I'm going to show it over this side here. So the integrations for this, we have to apply the integration by parts. That will be equal to, I'm going to proceed from here. You can see that that is actually equal to this. It will be u ln u square 1 plus pi, subtract off with, okay, subtract off with, um, the u is actually 2u ln u 1 over u. Okay, now I hope that you are clear how to differentiate this. Okay, if you are not clear, I'm going to show you how to differentiate it. Okay, before we proceed further. So in this case, how do we actually get this um, result? Okay, now first of all, we are actually applying the integration by parts. Okay, I'm going to show you the integration by parts one more time here. Okay, now I'm going to pause here for a while. I'm going to clean up all the sections here, just to let you know that we started off from the original formula for the area enclosed by the polar curve, and then we substitute the whatever that is given here, r, and then by using substitutions, we end up with this form that we need to apply integration by parts with over here. Okay, I'm going to finish off this, then I'm going to show you how the integration by parts is actually being carried out step by step for some of you who would like to follow a systematic method. For some of you who can see the shortcut, now bear with me, we can try to work this out here. So let me try to finish that. From here, we have 1 plus pi ln 1 plus pi square, subtract off with a 1. Okay, so when you put a 1 there, the ln is actually a 0. Okay, now that's the first part. And then the second part of this integration, once you got this, you can actually simplify that, and then eventually we will end up here. Okay, we are going to end up at here. We can take out the 2 from 1 to 1 plus pi, and then the u can be cancelled out, only left with ln u du. Okay, and then there you have it, and then you can further proceed on with this. So that is 1 plus pi ln square and then this is 2. You can further perform the integration by parts one more round, which is ln u 1 plus pi. I would say put a round bracket here, and then subtract off with after you've done the integration by parts, we will end up with what do we have here? We have u 1 over u that cancels out, which is actually just 1, and then you can um, integrate that using this 1 plus pi. Okay, and then there you have it. Those are the integration by parts that we are having at this point. Okay, now I'm going to pause there. I'm going to finish up the entire um, integrations before I'm going to show you how that integration by parts is being performed step by step. Right? we don't need this anymore. We're going to erase all this up. Okay, initial line, we don't need that anymore. This part, we don't need this anymore. Alright, now next I'm going to just copy down whatever we have. Therefore, the area is given by half 1 plus pi ln 1 plus pi here square. Subtract off with 2 times of this. Okay, that is typically if I'm going to just rewrite that everything down so that we can refer to that in a while. Okay, and then finally plus a 2 u 1 plus pi, and then close the bracket. Alright, now that is the area that we are interested in. Let me try to simplify that. So here, if I try to simplify this, when I substitute 1, definitely is going to be a 0, and then that would typically give me a 2 1 plus pi ln 1 plus pi here. Okay, and then finally this part here, I will end up with a 1 plus pi minus a 1. I will get 2 pi. Okay, and then we are almost there. From here, we can join these two together. Okay, let me see. I'm going to erase off this. We don't need this anymore. Okay, now let's try to join these two together. We can factorize this out. So once we factorize that out, we have 1 plus pi ln 1 plus pi. Okay, and then that will be, let me see, we have therefore we have, once we factorize that, we will have ln 1 plus pi here. Okay, and then from here we are going to minus off 2. Okay, that should be minus a 2, and then that will be here, and then plus a pi there. So if you substitute the expand the half onto this, we have a pi. And then let me check one more time. 1 plus pi ln 2 minus 2 plus pi. And then there you have it. That is the area enclosed by the curve and the initial line. Right? Now I hope that is clear. Now next I'm going to pause for a while. I'm going to show you how that integration by parts can be performed. Right? Now I'm going to do that separately for some of you who like to follow through. Alright, now let me show you how the integration by part has been performed. This is the area that we are looking at. It's half r squared d theta. We're going to substitute the r inside here. The entire integrations can be written in terms of u. That will be negative because there's a negative here. Now that will be 1 plus pi until 1 here. And then because there's a negative here, we can switch it around. We can rewrite as half ln u square d du. I think I forgot to change this. It's supposed to be u. Hold on. Du. Okay. We can change that to 1 plus pi 1 here. Okay. Now for the integration by parts. Okay, usually uh, we can let no, in this case we can let like let u equal to this. We can let I'm going to let u equal to what we're looking at. Let u equal to ln u square. Okay, and then from here we can differentiate this first. Du du I mean this is already u. If I let u equal to this, that will look a bit weird. So maybe I'm going to label that as let me see that will be w then. Let me label it w. So let w equal to this dw du will be, you're going to apply the chain rule. That will be 2 ln u, and then after that we're going to differentiate this ln u, which give us 1 over u. Okay, now that's how it would actually look like at this point. So I'm going to put a bracket across. Okay, now that is w. And then at the same time, we're going to let v equal to 1. Okay, this is basically just time 1 over here. All right, and then from here, sorry, dv, I forgot that this is dv dx. Let dv dx is equal to 1. From here, we will be able to find out the v is equal to x here. Okay, I shouldn't be using x. I'm a bit blurred today. Okay, I shouldn't be using x because the one that I'm looking at is u itself. So I'm differentiating with respect to u. That should be a u itself. So dv du is equal to 1. Therefore, the v is equal to a u here. Okay. By using that integration by parts formula, okay, so we can actually rewrite this as in this form. So I can write it down using this symbol here. It will be um, a v. Okay, let me see. Is it a v? Yes, correct. It is a v. V vw. Okay, so the formula for integration by part is vw minus of v dw du, and then differentiate that with integrate that with respect to u again from here. Now that is the formula for integration by parts. From here you can substitute all this value that we have. That is v equal to u. That will be u. W is ln u square. Okay, and then subtract all with v again. That is u. dw du is given by this 2 ln u 1 over u, and then integrate that with respect to u again. I did not put in the upper boundary and lower boundary. We are going to finalize it before we put in the lower boundary and upper boundary. So from here you have ln u square, and then that typically become, okay, subtract, and then you can cancel off all these sections here, and then that will give us ln u du, integrate that. Okay, and then don't forget, I'm just referring to this section here by considering this integration alone. Okay, so this integration alone would actually give us this one here. Just let me, this is ln u square du is actually equal to this. Alright, so the entire integrations of ln u square using integration by parts is given by this, and then eventually we reach this section here up to here. And then can I perform integration by parts further? Yes, of course you can. By looking at this, by considering this, you can let your w again equal to ln u, and then your dw du is equal to 1 over u. And then the same thing, we're going to let our dv du be equal to 1. And then for that, our v will be equal to u again. And then substitute in the same formula, we will end up with this. That is u ln u square, subtract off with a 2. And then this entire thing will be vw. So vw, that will be u ln u. And then subtract off with what we have as u 1 over u du. Okay, and then finally we're going to simplify this. Plus 2. You can see that the u has already been cancelled off in this case, and then therefore there's only left with 2. 2 integration of 1 is basically just u. And then that's it. That's the integration itself. And then once you have done that, you can actually put in the lower boundary and the upper boundary. Therefore, you can see that 1 over 2 ln u square, integrate that with respect to u from 1 to 1 plus here. That is typically the same as half. All you need to do is just put in all the upper boundary and lower boundary here. Okay, from here we're going to put in the lower boundary and the upper boundary. And then finally, you can simplify this as 1 over 2 as what is indicated in the answer itself. 1 plus pi here, ln 1 plus pi, and then you have ln 1 plus pi minus 2 plus a pi. And then there you have it, right? So this is the overall process of applying integration by parts, step by step, right? Now, I hope that is useful. We're going to move on to the next question shortly. All right, let's look at section C of this question 5. Now, I redraw this curve again. Okay, this curve is the one that we have drew for the section A. And this is how it looked like. And then for this section, we were asked to show that at the point of C, furthest from the initial line. Now, we know that the initial line is this line here. This is initial line. Now we want to find out the furthest, the point on the curve that is furthest from the initial line. Now therefore, the furthest means is a tangent, right? So we're going to find out which point that is sort of the tangents to this line here. So it should be somewhere here. In order to apply the idea of tangent, we know that this line must be horizontal because the gradient of this tangent must be the same as the gradient of the initial line, which means dy dx must be equal to 0 here. Now that's the main concept that we're going to apply here. Okay, now in order to perform dy dx, we need to apply the relationship between the Cartesian equation and the polar equation. Right, therefore the relationship between the polar and the Cartesian is given as such, but if you have forgotten this, you can always sketch out the Cartesian plane and then assume that there is a polar point given as P, and then the polar coordinate usually is labeled as R theta. It means that the point P is located at a distance of R and then making an angle theta with the initial line here. Now, what is the relationship between the X component and the Y component on the Cartesian plane then? You can draw a right angled triangle here, and then from there we can build up the relationship between the Cartesian component X and Y with R and theta. Therefore, we know that X is equal to R cos theta, and then our R is this, so we're going to put that in. Cos theta. And then by differentiating this with respect to theta, we will have, we're going to differentiate the cos first, then there will be a negative sign theta ln. Okay, following by differentiating the ln itself, I will have negative cos theta divided by 1 plus pi minus theta here. Okay, and then there you have it. There's the differentiation of the component x with respect to theta. Now I'm going to build another relationship between the y and the r and theta. That's given as r sine theta. Therefore, in this case, I can rewrite as ln 1 plus pi minus theta sine theta. From here, the differentiation is given by, now that is quite direct. From here we are going to differentiate the sign, which will give us a cos ln 1 plus pi minus a theta. Okay, and then after that I'm going to differentiate the ln now, which is negative sine divided by 1 plus pi minus theta. And then we know that dy dx is given by the chain rule, which is dy d theta divided by dx d theta. And then in order to get the point that is furthest from the initial line, we need to solve the dy dx equal to 0. That is when we have a tangent that is touching the curve at the point that is furthest from the initial line. Now from here it's quite obvious that you can simplify as dy d theta as in equal to 0 here. Therefore, all you need to do is just assign your dy d theta equal to 0. Right. Now from here we have, I'm going to simplify all this. We will have a cosine theta ln 1 plus pi minus theta minus a sine over 1 plus pi minus theta is equal to 0. And then by a bit of rearrangement, we will find that 1 plus pi minus theta ln 1 plus pi minus theta minus tangent is equal to 0. And then there you have it. We managed to prove that the point that is furthest from the initial line is obtained by solving this equation here. Right? And then lastly, we need to verify that these equations will have a roots between. In order to verify that the roots is actually located between 1.2 and 1.3, we can label this as a functions of data. And then we are going to substitute that 1.2 into this particular um, equation here. And then if you substitute this, let me try to see what we have here. We have, okay, just let me check that out. I'm going to pause for a while. You can do your calculation here, like when you substitute data equal to 1.2, are you expecting to get a positive value or a negative, right? So I'm going to pause for a while. All right, from the calculator that I have used to compute this, I found that when I substitute 1.2 into these functions, I got a positive value. If I'm not mistaken, it's around 0.6 something. So this is positive value. And then I'm going to repeat the same process for 1.3. And then I found that I got a negative 0.64 around there. So this is less than 0. Now, for this, I noticed that there's a sign change. So I'll write down there is a sign change. Because there's a sign change, therefore, we managed to verify that the roots will be in between 1.2 and 1.3. All right. The main reason as to why that is true is because assuming that this graph looks something like this, if we try 1.2 around here, is okay. Okay, let's assume that okay. Now that graph is a bit off. Just let me correct that so that I can explain it better. Now, in this case, assume that the graph look something like this. For instance, this is around 1.2 here. So we got ourselves a positive value, which is indicated by here. And then next, when we try 1.3, we obtain a negative value here. Now, because there is a sign change, one is positive, one is negative, definitely the curve will be crossing the x-axis. And then this is where the roots alpha is actually located. And then you must make sure that there's a sign change. Then we can verify that the roots is between. Therefore, roots is between 1.2 and 1.3. Okay, now I hope that is clear. That's the last part for this section, question 5. Stay tuned for the next question. All right, let's take a look at question 6 now. Let A be a positive constant. We need to sketch the curve C1, which is given by this equation y equal to x minus a divided by x minus 2a. This is a rational function. Now, before we start to sketch that graph, we need to set up a few guidelines. The first one being the y-intercept. Now, to find out the y-intercept is quite direct. We just need to let our x equal to 0 here. Therefore, we found that the y is actually given by a half here because this is 0. The a can be simplified. And then there you have it. All right, now secondly, we are going to find out if there's any x-intercept. Now the same thing, we're going to let y equal to 0 now instead of letting x equal to 0. By doing so, we have x minus a divided by x minus 2a is equal to 0. And then now we need to set a restriction here where the x cannot be equal to 2a. Right now, therefore, indirectly, that gives us an idea that x minus 2a is actually the asymptote. Right, I'm going to write down the informations in the next stage here. All right, now before that, let's assume that x cannot be equal to 2a. Therefore, that would actually lead us to the solutions being x equal to a here. And then this is our x-intercept. All right. Now next we're going to look at if there's any asymptotes. We have already identified one. All right, now asymptotes. The first one is the vertical asymptote. So the first one is x equal to a. All right, because in order for these equations to exist, the x cannot be equal to 2a. All right, I hope that's clear. Now next we're going to check out if there's any horizontal asymptotes. Now usually the way I would prefer to do it would be to sort of convert this rational function, improper rational function, into a proper rational function. That's how we are going to um, carry out this operation properly, right? So in order to do that, you can, in order to convert this improper fraction into a proper fractions, you can use a very simple rule, long polynomial division. So I'm going to write the process down here. We're going to take x minus a divided by x minus 2a here. And then that being an a. Therefore, from here, we can actually write that equation. We can rewrite this equation as y equal to 1 plus a over x minus 2a. All right. Now, having this form here, it will be easier for us to analyze its horizontal asymptote. As x is approaching either positive or negative infinity, we know that this term here would converge to 0. Therefore, the y would approach a 1. And then we can say that the horizontal asymptote, the horizontal is y equal to a 1 here. Now that will be our horizontal asymptote, right? Okay, I hope that is clear. And then of course, lastly, you might be interested to figure if there is any stationary points. So the last one is to check out whether there's any stationary points. To analyze the stationary points here, we are going to differentiate this. It's better to differentiate this form than differentiating this. We don't have to apply too much rules of differentiation here. Just by differentiating this, we will have negative a over x minus 2a square. All right. Now we know that these differentiations cannot be 0, because if we allow dy dx equal to 0 here, there is no solution. Because there is no solutions, therefore we can conclude that there is no stationary points. And now we are ready to sketch the graph. So first of all, it's always easier to highlight the vertical asymptotes here. So we have x equal to 2a. Now I'm going to write that down. Asymptotes usually is labeled using broken lines. So here I'll label that as x equal to 2a. And then we also have another horizontal asymptote at x equal to 1. Yes, x equal to 1. Okay. Okay, I'm going to say that x equal to 1 most probably will be somewhere here, for instance. So this is y equal to 1. Alright, now those are the two asymptotes that we are going to present on the Cartesian plane. And then other than that, we don't have any stationary point. We do have the y and x intercept. Now our x-intercept is at a, so this is 2a. The a must be somewhere here. And then we have a y-intercept at half. So this is 1. Most probably half will be somewhere here. And then therefore, the graph would typically look something like this. I'm going to sketch it out. Right, there's the first part, and then the second part will look something like this. You need to pass through the half, and then you need to pass through the A here, and then it would diverge to infinity. Okay, now I hope that is clear. That's how the graph of y equal to x minus a over x minus 2a would actually look like in this case, right? Now I hope that is clear at this point. I'm going to move on to the next sections shortly. Right, let's look at section B of question 6 here. Next, we have been given the second curve labeled as C2 has these equations. That's the square of the equations that is found in the first question there. And then we have curve C is the modulus of that functions that we have found in part A. Now, the task that we are supposed to perform here would be B1, find the coordinates of any stationary points of C2. Any stationary points of C2. And then secondly, we're going to find also the coordinates of any points of intersection between C and 3 here. C2 and C3, sorry. Right. Let's start with B1. All right, stationary points of C2. So let's concentrate on the equations of C2 here. This is C2. All right, now if you still remember the partial fractions for this, we can actually make use of this partial fraction. We can rewrite as A over x2a here, square. It'll be much more easier to differentiate in this case. It will be much more easier if you actually expand this. All right, now let me expand this because this is just a square. And then finally we have all right, once you have this format, it's easier to differentiate. Now that would typically be and then this one being oops, sorry, let me correct that. That would typically be negative a here. Did I get it right? Let me check. Did I get it right? Hold on. Let me see if I get it right. This is correct. And then, yes, this one is a 2a square. Sorry, I made a mistake here. So it's a 2a square minus x minus 2a cube here. Yep. Now, that will be our differentiation. And then in order to locate the stationary points, we will have to equate this equal to a 0 here. And then now setting the x not equal to 2a. Right? Let's make assumptions that the x cannot be equal to a because the x equal to a is the asymptote itself. Now, because x cannot be equal to 2a, let's make that a restriction here. Therefore, we can multiply both sides by x minus 2a square here, just to get rid of this denominator, because we have already set this restriction here. We will end up with negative 2a, and then here we will have 2a square over x minus 2a, for instance. This is how it look like. And then you can further simplify this a, because a is a positive constant. Okay, let's assume that a is not equal to 0, because if a is equal to 0, then therefore that might not fit in rational functions here, right? Okay, now for that we can simplify this as -1 minus a over x minus 2a equal to a 0 here. And then lastly, we can simplify this as a equal to negative x minus 2a. And then finally we can find the solutions for x here. So therefore, the x is given as, okay, we have 2a here is equal to a. Right. Now, if you like this method, you can actually use it. If you are not keen on this method, we can also use the alternative method that I'm going to show you at the side here. Now, therefore, this is the um, stationary stationary point of C2. And then this is the only one. Don't forget, we have to get the y coordinate when x is equal to a. We know that by substituting a back into here, the y is equal to 0 here, right? Now, if you are interested to find out what type of stationary point is this, we can just simply use a line graph to determine the nature of this stationary point. Now, to do that, all we need to do is draw a line here. This line represent the value of x. We have a critical value a here. We're going to label that as a. And then this graph basically represent the gradient dy dx. Now we can try substitute a value that is greater than a into our gradient function here. Take for instance, right? Now you can substitute, for instance, the asymptote is somewhere here, which is x equal to 2a. So it might be wise to substitute anything between a to 2a here. Let's choose like 0.5a then, positive 0.5a then. Okay, oh sorry, 0.5a is on the left hand side. We might want to choose like 1.5a. Okay, now if you try to put 1.5a into this expression, these sections will be a negative. And then you can put in these expressions 1.5a here, and then that would actually cause a positive number here. And then therefore we are going to try out. I'm going to write down at the side, and then we are going to see whether we get a positive or negative here. Okay, now negative 2a, that will be like we choose a 1.5a, so 1.5a, that will be 0.5a square here. Subtract off with 2a square, that is 1.5 minus this is again is negative 0.5a cube. Here I just dropped the negative here because if we square that, it will still be the same. And then from here we will get like a 2 that will actually give us 0.25a. Okay, and then here it will be a plus a 2, and then 0.25a also. All right, is that correct? Let me check here. 0.25 a positive, oh sorry, this is a cubic. Okay, I almost missed that out, right? Therefore we have something like this. Let me correct that. So that will be a 0.25 and then another 0.5, so that will be 0.125a then. Okay, and then from here it's very obvious that this is much more larger than a 0, and then therefore this will have a positive gradient, right? And then by repeating that for value that is less than a, take for instance if we choose like 0.5a, now we can try to substitute that 0.5a, that will give us negative 1.5a square, subtract off with 2a square, and then the same thing, negative 1.5a cube. From here we will get 2 over 2.25 a, and then from here we will get like 2 over 1.5 to the power 3 a here. and then sorry, I forgot the negative here. And then from here, if you try to tabulate using your calculator, you will find that this is actually less than 0. Therefore, we have a negative gradient here. And then lastly, negative gradient means it's going down. And then at the critical point here, the gradient is 0. And then we have a gradient positive, it's going upward. So most probably, the nature of this stationary point is local minimum. All right, now I hope that is clear. All right, now I'm going to show you another alternative methods to obtain the stationary point if you are not interested to use this method here. All right, I'm going to erase this. I'm going to show you the alternative method to perform the differentiation. So this is the second method. We still have the y. Instead, I'm going to start the y from here instead. This can be written as this. We know that we have already obtained the partial fraction. All right. Now all we need to do is just differentiate this without expanding this. By using chain rule, we'll get something like this. And then after that, differentiations of this section. And then there you have it, our dy dx. Right? And then the same thing, we're going to equate that equal to 0 in order to locate the stationary point. And then making that restrictions available, we can multiply both sides by x minus 2a here. Okay, now I'm going to do a bit of simplification first. From here, once I multiply with x minus 2a both sides, I will only have a 2a 1 plus a x minus 2a here equal to a 0 here. Now, by all means, you can remove the a if you like, making assumptions that the a is not equal to 0 here. Right? Therefore, and then you can also remove the 2, and then we end up with 1 plus a x minus 2a, which eventually end up with the same expressions that we have here, the same equations, and then we found that x is equal to a. This is exactly the same answer that we got from previous methods here. And then by substitute x equal to a back into the original equations, you will be able to obtain the y coordinates for the stationary point, which is obviously a 0. Okay, now that's all for this section B1. All right, now I hope that is clear. I'm going to pause for a while. I'm going to show you the second section, 6B2, shortly. Okay, section 6B2 here. We need to find the coordinates of any points or intersections between the curve C2 and curve C3 here. All right, now because this is a absolute value function or modulus function here, we are going to break down the analysis into two cases. The first case would be, we will equate this equation here, y1 equal to y2 using case 1. That will be here. Okay, we assume that is a positive value at this point, and then making the restriction x is cannot be equal to 2a because it's asymptote here. We can reduce the x minus 2a here. Therefore, we have we can also reduce the x minus a. Okay. Now, therefore, in this case, let's assume that, okay, let's simplify this as x minus a square, and then equal to x minus a. If we multiply x minus 2a squared both sides, therefore we end up with this. Okay, now that's how it looked like. And then after that, we're going to factorize this. Now we're going to bring everything to the left hand side, and then we can factorize this as, and then there you have it. This is the simplifications that we can get. All right. And then therefore we found that because a cannot be equal to 0, there's also um, my assumption at this point. Okay, it should be correct, because if a is equal to 0, then it will not form a proper rational functions that we have here, right? Therefore the only solutions that we can get for this case here is x equal to a. Therefore, C2 and C3 intersect at this x coordinate of x equal to a. And then by substitute this x equal to a back into the original equation, either this or this one here, it will yield y equals 0. Now, that is exactly the same stationary positions where this intersection is located, right? Now, case 1. Now, we're going to proceed on to case 2 now. Now, for case 2, we will have x minus a, x minus 2a square equal to a negative of this. All right. And then by carrying out the same procedure here, we will have this. I'm going to multiply both sides by x minus 2 square. And then carry out the same operations again. I'm going to bring everything to the left hand side and factorize it. And then from here, I can conclude that as x minus a, and then this can be simplified into 2x minus 3a is equal to 0 here. Now we have already found out one of the intersection points just now. X is equal to a, so we don't need to worry about this. The second one being 3 over 2a. And then we know that when we substitute x equal to a into the equation here, we will end up with 0 for this particular set. And then for the second one, we're going to substitute this one back into here. The same thing, we will get, I'm going to work out the calculations at the side here. So the y is basically 3 over 2a minus a here, divided by 3 over 2a minus 2a, and then the entire expression is square. Now that will be a 1/4, and then this part will be a 1/4 also. Okay, you can see that is 1/4. Just let me check properly. This is a negative 1 over 2 actually. It's negative 1 over 2, but if you square that, that will become 1 over 4. And then eventually, of course, we are squaring this. It is 1. Therefore, the second intersection is at x equal to 3 over 2a, and the y coordinate is 1 here. Therefore, we can conclude that, okay, I'm going to write the conclusions over here. The coordinates of their intersections. So intersection between C2 and C3 are given as, I'm going to label that as position A, for instance, A0, and B 3 over 2A 1 here. Alright, now I hope that is clear. We are done with section 6b 1 and 2. Now we're going to move on to the next section shortly. All right, section C of question 6 here. We need to sketch both for the C2 and C3 on a single diagram, clearly identifying each curve, C2 and C3. Hence, find the sets of values of x for which it satisfies this inequality. Now, before I start to sketch the graph itself, I'd like to bring you back to the original curve that we have sketched at the section A there, which is given by y equal to x minus a over x minus 2a here. Now this is how it looked like originally, and then we just need to make a few adjustments to obtain. I think the easiest one to start with is the modulus graph. Now we just need to reflect the negative portion of the original curve here, so that it will be reflected in the line y equal to, sorry, in the line of the x-axis. Okay, so I'm going to reflect this. It will look something like this now. Yep, I'm going to reflect this. It will be something like this. Yep, that is how it will look like. And I'm going to remove off the original one so that it's not very messy to look at. So we don't need this anymore. All right, now that's how the graph of the modulus look like. So I'm going to label this graph here as y equal to x minus a, x minus 2a modulus here. All right. Okay, we are done. Then the second part is the more challenging one. Now the second one, I like to bring back some of the informations about this curve here before we start to sketch it. This is x equal to 2a. Now we know that for the curve y equal to x minus a over x minus 2a square, it has a stationary. We can list down some of the properties of this graph here. We know that there is a stationary point which is found at a0. And then we have even found out that this stationary point is a minimum. Now that is over here. So there is a minimum point over here for the curve C2. This is curve C3. So curve C2 has a stationary point at this point. And then we also found that there are like intersections between these two graph here. So the intersection, I'd like to write down one more time, intersection between C1 and C2 are first of all, they intersect at A0, which is point A just now, we labeled that, and then it also intersect at point B, which is 3 over 2A and a 1. Right, so it intersect at somewhere here, and then intersect at somewhere here. All right. Now, next, the graph. Okay, the graph is a square here, right? So you might want to try out to find some more extra informations for this graph before we start to finalize that. Now, the next informations that we can find out for this C2 is here. We can find the y-intercept maybe. So let x equal to 0. We found that the y is actually equal to a quarter, meaning that the graph will be passing through somewhere here. It will be lower a bit, right? And then it will also be intersecting at this point here. So most probably, I would say that the graph of this would look something like this. I'm going to try to sketch it as accurate as possible. So you can see that eventually this part of the graph would definitely reach the asymptote. but at this point I'm going to draw that it's going to come down here because this is a stationary point. So this part I did not draw it correctly. Hold on. Just let me trim it down a bit because it's a stationary point. So most probably it's going to go up somewhere here, and then it may actually reach the asymptotes again. But this is where it intersect. Now, bear in mind I did not draw this accurately, so maybe I'm going to trim this one down. Maybe it actually looks something like this. Okay, and then the last part of the graph is over here. You might be wondering how would the graph for these sections would actually look like. So we can give it a try. Okay, now if you let a more than sorry, x more than 3a, let's give it a try. So we are going to use trial and error. I'm going to write down trial and error. Okay, now by letting x equal to 3a, for instance, therefore the y itself will become, the y that we're referring to is here. There will be 3a minus a over 3a minus 2a, and then a square here. And then that would typically give us like a 4. A 4, right? So a 3, you will get a 4 here, right? But if you compare the original functions without the square itself, we would get a 2 instead. You will get a 2 instead. So which means the graph that we are looking at right now most probably will be higher than the original graph. So therefore, my guess would be look something like this, maybe. It will look something like this. Okay, let me redraw it again. That's a bit not very smooth. So let me try again, see whether it works more smoothly. It will look something like this. Yep, it will look something like this. And then definitely both of the graph will not intersect in this particular region. We have already found that the two graphs can only intersect at these two points here, which we have already found. One of them is here, the other one is here. Right? This is the y-intercept, which occur at, I'm going to write this one down at quarter here. All right, and then there you have it. That's how the graph actually look like at this point. Okay, now we're going to answer the last part now. Clearly identify each curve. Yes, we have done that. Hence, find the sets of value of x for which, now the way I will look at it graphically would be, we are looking at the modulus graph that is much more higher, um, that is much more higher than the graph of the um, a square here, right? So we are looking at the sections of the modulus graph, which is the blue one, that is much more higher than the green one. And then where could that be? All right, now if we check this region here, the green one is much more higher than the blue, so we are not going to take this region. And then for this region here, we found that the green one, right? So the green one is sort of still higher than the blue one for this particular region. I'm going to mark that region down. This region, I'm going to put a dotted line here. So we know that this is x equal to 3 over 2a. Okay, for this particular region, the green curve, which is the quadratic, the square of these functions, still higher than the blue one. We're not going to take this region either. And then when we go down here, we notice that the blue one, right, the blue one, which is um, the modulus, the blue one is a modulus graph, is much more higher than the green one over here. And then at the same time, we notice that the blue one is also higher than the modulus function is also higher than the square of the original curve. Therefore, we are going to take all this region from x equal to 3 over 2a all the way to the left, because we found that the blue one, which is represented by the modulus function, is much more higher than the green function, which is represented by this one here. I put it down in green so that you can recognize which graph that we are referring to. This one will be the blue one. We only need to look at the region where the blue graph is, or blue curve is higher than the green one. Okay, so therefore you will cover all this region all the way to the left, starting from x equal to 3 over 2a, right? Therefore, we will say that the sets of value, the solutions, here I will write down solution to this equation, to this inequality, is actually given by x are all real values, or I can write down x actually represent all the values from, you can actually write down from all the way from 3 over 2a to negative infinity. So this is 3 over 2a here. So you can write it down in this form. I think I wrote down wrongly. Hold on. Let me correct my mistake here. It should be, because they are using less than or equal to, so I should actually include this as an inclusion sign. Or you can actually write down x or less than or equal to 3 over 2a. Okay, and then there you have it. That is, or that are the sets of solutions for this inequality. I hope that is clear. And then that's it. That's complete solutions for question 6. We're going to go down to the last question 7 shortly. All right, let's take a look at the last question here, 7. We have section A and B, I think. All right. Now, the points A, B, C have a position vector given as negative 2i, j, 2j minus k. The second point is given as negative 2i, j plus 2k, and then the last position vector is given as 0i, negative 2j plus k here. Now I will write down the position vector over here just for us to. Now personally, I prefer the column vector form, so I can write it down as OA, the position vector as negative 2, 2, and negative 1 here. And then I can rewrite my position vector OB as negative 2, 1, and a 2 here. And then lastly, I can rewrite my position vector C as, don't forget, I'll be very mindful with there's no I component, but there's a J and a K here. All right, and then there you have it. Those are the position vector given to us relative to O. We need to find the equation of the plane ABC given your answer in this Cartesian form. Now for the plane that is formed by ABC, I'm going to draw out the shape of the plane. Roughly we get an idea what we are looking at. So take for instance, the ABC will look something like this. Okay, this is, let me draw it down properly. So maybe A will look something like this, B will look something like this, for instance. So this is A, this is B, this is C, for instance. Okay, and then what we need to form the equation of the plane is basically the normal, the normal to the plane. Let's draw this normal something like this. This is the normal to the plane ABC. Normal means is 90 degree to the surface of the plane ABC here. Okay, now we are going to label this as N1 vector. I shouldn't have labeled that as a unit vector form. I'll just label that as a normal vector. Okay, that is pointing in that's pointing perpendicular, that's pointing at 90 degree to the surface of the plane ABC here. Okay. Now to start with that, we need to get the normal to this. How to get the normal to this plane? We need to get a few informations before we can get the normal here. Firstly, we need the AV vector. You can actually choose a AV vector. Say for instance, we can choose AV vector and AC. And then we can work out the normal by using the vector products. So I'm going to choose a AB. Let's work out the relative vectors for AB. In this case, AB is basically negative OA. Okay, so we just need to add these two up here, and then that basically equal to, I'm going to do that very quickly here. That will be 2, negative 2, 1, and then end up with negative 2, 1, 2 here. And then we will end up with a 0, negative 1, and a 3. And then next we're going to repeat that for relative vectors or AC. Okay, AC is this. And then performing the same result or same procedure here. We will end up with 0, negative 2, and 1. And then that would be 2, negative 4, and a 2 here. Therefore, the normal, to get the normal to the plane itself, this is the normal, is given by the vector products of AB cross with AC here. Now there are many ways to obtain the uh, vector product, right? So I'm going to show you the most traditional way to do it, which look very similar to the determinant of a matrix, right? That actually look like I, J, K, and then we're going to fill in the position, the relative vectors for AB, which is 0, negative 1, and 3. And then next we're going to fill in the AC, which is 2, negative 4, and a 2 here. And then we're going to perform the this determinant process. So from here, we will get like this is an I. We're going to get the determinant for this particular I here, or you can say that we're going to get um, the minor that corresponds to I here. Right? So that is typically negative 1, 3, negative 4, 2 here. And then minus off based on the alternating sign for determinant. That will be the minor for 0, 3, 2, 2. It's a minor for J. Let me check if I got it correct. Yep. And then lastly, we have the K. Then the minor for K is 0, negative 1, 2, negative 4 here. And then lastly, we just need to finish the compute the determinant. That is negative 2 plus 12. So that will be a 10, 10i. And then here we have negative 6, which is 6j. And then finally we have 2k here. Or we can write it down as 10, 6, and then a 2. And then there you have it. That's our normal to this plane here. So I can actually write this normal down over here. That is 10, 6, and then a 2. Right, and then there you have it. This is one way, or you can do it using a vector directly without going through the determinant process. Okay, we can do it this way. All right, hopefully I got this correct. Now we can copy down exactly as what we have here, negative 1, a 3, cross with or vector product with is okay. And then all we need to do for this method is, if you want to get the um, sort of the determinant or the minor for the first I itself, we can we can sort of close out, or you cancel off, like mentally close out the 0 2. Don't look at the 0 2 itself, okay, and then just look at this as your uh, determinant. So let's calculate this determinant here. All right, then this determinant will actually show us a 10. So you just fill in the 10. And then next, we're going to proceed on to the second row. The second row, you have to close out or cross out this -4 and -1 and 4. Just cross out it. Mentally cross out. Now you only see 0 2 and 3 2, and then try to perform the determinant computations for 0 2 and 3 2 here, and then you will end up with -6. But don't forget the second row, we also need to use the alternating sign. That will be a 6. And then lastly, you're going to cross out the last row here, and then get the determinant for 0 2, -1 and -4, which actually yield a 2 here. And then there you have it. That is the same normal to the plane ABC. So it's upon your liking, yeah, which way you want to use, right? Okay, now we have done getting the normal, but we have not actually obtained the equation for the plane, right? Now I'm going to erase all this. I'm going to proceed on to obtain the equation of plane. Okay, now I'm going to erase all this. We don't need this anymore. Right, now the equation of a plane in the vector form is given by now plane A, B, C is given by this general standard formula, which is given as the general points that are located on the plane itself. This is a scalar product with the normal vector that is perpendicular to the surface of the plane ABC, and then it must be the same as any point that is located on the plane itself. You can choose either A, B, or C, it doesn't matter, and then perform the scalar product again with the uh, normal vector again. Right, that's how we are going to carry that out. And then from here we are going to write that down as the normal has been 10 6 2. The point A, you can choose any one of your liking. So maybe for this purpose here, we're going to use A instead. It will be easier to relate, right? So we're going to use the A here because it's easier to relate. I'm going to write that down. Position vector for, oops, sorry. Just let me clean this up. Position vector for A, -1 here. And then perform the scalar product with the vector normal to the plane. Right, that will be a -20, a 12, and then a -2 here. From here, we will get a -10. Let me see whether that's correct. Yeah, -22, -10. Yep. So that's -10. From here, we can rewrite this as 10 6 2 equal to -10 here. Now that will be the vector form of the plane equation that represent the plane ABC. Now anyway, for this question they want the plane equation in the Cartesian form. Therefore we're going to convert the R, which which can be represented as x, y, z here, sets of all points located on the plane ABC, as -10. And then performing the same scalar product on the left hand side, it will lead us to this. And then finally simplifying this, we will get 5x plus 3y. Alright, and then there you have it. There's the equation of the plane that represent the plane ABC in the Cartesian form. I'm going to stress that again. This is the Cartesian form, or it could be in the vector form, depending on the question that you are having. Right? I'm going to move on to the section B shortly. All right, let's take a look at section B of this question 7. We need to find the acute angle between the plane OBC and ABC. We have the plane ABC here, and then we need to find out the angle between another plane with this plane ABC, OBC. Now, before I do that, I'm going to draw the plane OBC. Let's assume that the O is somewhere here, for instance, just as a reference, and then we have the OBC here. Now let's assume that the plane looks something like this. This is just a rough sketch here. And then for the plane OBC, it also have its own normal. So let's assume that the normal is somewhere here. Okay, that is 90 degrees here. This is, I'm going to label that as N2, normal to the plane OBC here. Now we are interested to get the angle between the plane here. There are two choices of the angle depending on how you would like to describe your angle here. Either you describe as obtuse or acute. So take for instance, based on this drawing, you can see that if I'm interested to get the angle between the two planes here, most probably I'm going to get like this angle theta. But I noticed that the angle theta based on my drawing would be an obtuse angle. Therefore, where is that acute angle between the two planes then? So the acute angle will be somewhere here. I'm going to extend this line further. Now that acute angle will be somewhere here. I label that as alpha here. Now that will be the acute angle. And then knowing that this is the acute angle that we want to find, this acute angle is exactly the same as this angle here, because we know that theta plus alpha, that the relationship between the angle is theta plus alpha must be equal to a pi here, or 180 degree. And then we notice that from this straight line here, this is actually straight line, this is the straight line, so that angle theta plus alpha must be equal to 180 degree. Therefore, our objective is to obtain this alpha, which is the acute angle between the plane ABC and OBC here. Now I hope conceptually you are clear with this. Once you can get this visual perspective on to your mindset, then we are ready to apply the algebraic to get the actual acute angle here, right? Okay, let's get started with this. In order to obtain the angle between these two, normal is quite easy. We can actually make use of the scalar products formula. We know that the cosine alpha is given as n1 dot with n2, and then divided by the magnitude of the normal to the plane itself. Okay, there you have it. All right, all we need to do is just calculate this separately, and then we are going to substitute it over here. Now I'm going to do this separately so that we can substitute it in back in here. I'm going to do the first one, n1 dot with n2. Okay, that's a scalar product between n1 and n2. Right, now the only informations I don't have at this point is my n2. Do you see that? When I try to work with this, I don't really know what is my n2. So therefore, it's always good practice to find out n2 first. Okay, to find out n2, we're going to go through the same process like before. We're going to obtain n2. In this case, we can use the vector OB and OC directly, which is more direct. So I can say that my n2 normal vector is actually given by OB vector product with OC. Okay, now that will be my normal to the plane OBC here. And then I'm going to substitute that, all the informations that I have. And then take a bit of shortcut from here. I would have a 5. And then secondly, I will have positive 2, and then lastly, I will have a 4 here. Now that will be the normal to the plane OBC. Once I have obtained that, I'm going to come back here again. I'm going to proceed on with the dot product or the scalar product between the vectors between these two planes. That will be n1 dot product with n2 here. I have found my n1 previously, which is 10, 6, 2. Then I'm going to perform a dot product with 5, 2, 4 here. And then that typically is 50, 12, and then finally an 8. That would give me a 70 there. Right. And then there you have it. There's the scalar product between the normal vectors. And then now I'm going to calculate the magnitude for this separately before I try to substitute it into the formula to obtain the angle alpha. And then for this, it will be 10 square plus 6 square plus 2 square square root here. Okay, I try to use my calculator on this, and then let's see what are we having at this point. So that is like square root of 100, and then with with a 4 there. Okay, now that basically is like I'm going to write this one down first as in the form of cert. That would actually give me like 140. I'll just keep it as it is without simplification. And then after that, my n2 magnitude of m2 is 5 square, 2 square, and then 4 square. And then that would be like let me see, 25, 29, and then 16. Okay, that will be 45 then. Okay, just let me double check in case I got this wrong. Okay, it is 45. I'm going to keep it as it is without simplification. Okay, now finally, all I need to do is just substitute all the variables that I have already computed and then substitute into a formula for cosine alpha. Therefore, cosine alpha is equal to the scalar product, which is 70 over 140, 45 here. Okay, and then that is how it would actually look like in this case. I can try to simplify this a bit. Let me see what can I do with this. Now that is 1790. That is a cert is about cert 7 over let me see here, 90, 70, that's a 9. Or is simply a square root of 7 over 3. Alright, now just let me double check if that is correct. Let me see that there's 70 by 2 there, so there's a 70. We have 90 here. Okay, and then therefore from here I can obtain the acute angle for alpha, which is inverse cosine root 7 over 3 here. And then that would actually give me this one. I really need a calculator on this now. Let me see here. It's an inverse of, oops, sorry, let me clear that. Inverse cosine of square root of 7 divided by the 3 here. Okay, I'm getting 28.1. In the final exam, usually we will tend to leave it to the nearest three significant figures or more. Therefore, there you have it. There's the acute angle between the plane OBC and ABC, 28.1. I hope that is clear. Right? I'm going to move on to the last section shortly. All right, let's look at question C, the last part of question 7, which is our last questions today. Okay, now there is a extra point D has this position vector Ti minus j. Given that the shortest distance between the lines AB and CD is cert 10, we need to find out the value of t here. Now here I have already pre-drawn the line AB and CD here. Right. Now, there are points like A, B, and C and D on the line itself. All right. How are we going to find out the shortest distance? Using vector method here, we can do something like this. I can draw a line that is connecting this A and C together. Okay, I'm going to label that as vector AC. And then next, I'm going to find out the normal vector. So the vector that is normal to both of this line. Okay, both this line here. Okay, now how do we find the normal that is perpendicular to both of these straight line? Okay, now we can use the vector product. Okay, in order to get the normal vector between the two skewed lines here, we have to use the vector product. So the vector product is here. We're going to take the AB cross with CD here. So the AB we have already worked it out just now. We have AB as, okay, hopefully I still remember. I'm going to rewrite the AB that we have already obtained previously. That is yep, just let me rewrite that again in case I made mistake. So 2, -2, a 1, and then add up with a b, which is -2, 1, and 2. Just let me check one more time if I got it correct. Okay, that will be a 0, a -1, and then a 3. Now that will be the vector AB, and then after that we have to get our vector CD now. So CD, that will be a C, so that is -2 and then -1 here, plus the D. The D is given as a T, a -1, and a 0. Therefore, we can rewrite that as T, 1, and -1 here. Alright, now in order to get the normal vector between the two skewed lines, okay, I'm going to label this as the normal vector. The normal vector is given by, I'm going to write it down here. Normal vector is given by AB cross with CD here. Okay, and then from there we can put this one in as 0, -1, 3, CD. Right, now in a moment you will see why we need to use the normal vector between the two skewed lines. Alright, now let me finish calculating the vector product here. We will have, let me see here, -2, and then right after that we have a 3t, and then finally we will have a t here. Okay, and then there you have it. Our intentions of getting this normal vector is here. We are trying to find out the angle between the normal vector between the two lines and this vector AC. Okay, now why do we need to know that? Because we can get the shortest distance over here. The shortest distance is given as this. I'm going to write it down here. The shortest distance, because this is a right angled triangle, is perpendicular to both of the line. Therefore, the shortest distance D can be given by AC, the magnitude of AC cosine theta there. That is the one that we want to achieve in a while. How can we get that? All right, now this is the way to do it. Based on the angle theta there, we know that AC scalar product with the normal vector is equal to this formula that we have been using all this while, cosine, because that is the angle between the two vectors, subtend and angle theta. Therefore, we use cosine here. And then if you rearrange a bit here, if I rearrange, you will notice that AC multiplied with cosine is actually D. Therefore, I can modify a bit here. I'm going to write down that is actually D multiplied by the magnitude of N. Therefore, shortest distance, right? Shortest distance will be given by D. This is D is equal to AC scalar product with N divided by its own magnitude. That's where the formula for the shortest distance actually came about, right? So from here, all I need to do is just substitute all the values that I have. I have already found the n. The only thing I miss out is the AC part. So I'm going to work out the AC over here. The AC is not a problem here. I just need to take my negative OA and then with C itself. So with the OC, and then I will have 2, -4, and then finally a 2 there. Alright, now that will be my vector AC. Just let me recheck that one more time in case I make any mistake here. Okay, cool. Now once we're done with this, our shortest distance D is basically the scalar product between AC and the normal vector and the magnitude of this normal here, which is a 4 9t squared plus t squared. And then we are given that the shortest distance between the two lines AB and CD is actually given by cert 10. Alright, now therefore we manage to form equations relate the t to this shortest distance, and then from here all we need to do is just solve this equation and then obtain the solutions for t here. Okay, now I'm going to try this one out. This is yeah, don't forget we are finding magnitude, therefore it's always good to put down the modulus sign, because this is a modulus and then it represents the distance itself. Okay, now I'm going to perform the scalar product for my numerator. That is typically a -4, -12t, and then plus a 2t here over 4 plus 10t squared modulus here equal to cert 10. Alright, and then all I need to do is complete these solutions here, right? Okay, I'm going to give you time to process this. um, I'm going to simplify it in a while, right? So before that, let me erase these sections. We don't need this anymore. And then I'm going to write my solutions over here so that we can refer to that shortly. And then furthermore, we don't need this anymore. Okay, I'm going to write down here. All these can be performed over here. We have -4, negative 10t over 4 plus 10 square, 10t square equal to cert 10. All right, modulus here. And then all we need to do is to get rid of the square root, you can square both sides here. We will end up with like, in this case, you will get 4. Once you square, all these are positive. So I just write it down as positive here. And then that will be like a 10, a 4 plus 10t squared. Then you will get like 16 plus 80t plus 100 t squared is equal to 40 plus 100 t squared. And then from there we can solve it quite easily. Therefore the t you will be able to get as 3 over 10. You can see that there is actually like 24 over 80. Yeah, it's 24 over 80. I divide them by 8, that is 3 over 10. Now I hope that that is clear up to this point, how we can find the shortest distance between two lines here. And then that complete our sections today, okay, for paper 1. And then lastly, I would like to wish best of luck for those students who are taking exam in this November, shortly after this this week. Okay, best of luck, everyone. All right.